All right, let's begin. So today's topic of discussion will be center of mass and motion of center of mass. Okay, so until now, what we have looked at is motion of single particles, and we made a lot of assumptions. You might have not realized yet that we looked at motions of cars and people and objects, and what we did was we considered them to be as point particles. Okay, so we just reduced them to a point in space, and we said, okay, what are the forces acting on this point, and how this point is moving. But in reality, this is it's not that simple as it seems, right? Because objects are very complicated in shape. You have machines which are very complicated. You have a car, for example. It has doors, windows, it has tires, it has moving parts, right? So again, how is this possible that we can consider these complex objects and just write down a point for them and then deduce the forces? Okay, so let's look at this problem in detail. All right, and when we try to tackle a problem like this, we have to understand the concept of center of mass. Okay, so a center of mass is a point in the object, that as far as Newton laws is concerned, it acts as if all the mass of the object was concentrated at that point. Okay, so when we say center of mass, we are saying what is the position of this center of mass. Okay, so that is a specific point in the object where all of the mass is concentrated. Okay, so an object might move in certain path. Okay, and that motion of that object, we will reduce it to the motion of that point. Okay, and you will see how that actually works out. All right, so let's look at the equation that we are familiar with, which is the net force is equal to mass times acceleration. Okay, so we can write the three-dimensional form for acceleration, which is the double derivative with respect to time of the position of an object. Okay, so here m is the total mass of this complicated object. Okay, so it can be an object which doesn't have a regular shape. It is just a complicated shape like this, and now this object is moving in certain direction, and it has some acceleration. Okay, and the total mass is m. Okay, so this is capital M. Okay, so now we are trying to find that one position in this object, okay, from some frame of reference. So this will be our frame of reference, and this point that we are looking at is your r value, okay, of the position of this object with respect to some frame of reference. Okay, we also know that the net force is the change in the momentum, okay, which is the total momentum of the system. So now in our system, suppose we didn't have one object but we had many objects. Let's say this entire mass that is composed of the system is made of individual objects. Okay, so it is made of some individual object here, some object is here, some object is here. So I'm dividing the total mass into different categories of submass. Okay, and dividing it into as many objects or as many particles as I want. Okay, so in scenario like this, our total momentum will just be the sum of the mass times the velocity of each of these particles, right? So if this is 1, so whatever mass of this object 1 is, and the velocity of 1 plus this object 2, mass of 2 times velocity of 2, and so we can just add on this all these particles or this submass is present in this entire mass system. Okay, so this total mass, right, we had already said that the total mass is m, and if you look at the total momentum will be the sum of these momentums of each of these objects. Okay, and again for velocity we can write the formation in 3 dimension, which is d by dt of some position r. Okay, so now what we can do is we can equate these two, right? So we have net force is dp by dt. Okay, that is our side here. It will be equal to some m of j, right? So that is this value right here. Okay, and then we'll have take the derivative of this. So what we are doing is we are taking the derivative of this function here. Okay, so m of j is constant, or whatever it stays the same, and then you have d square by dt square of this r value. Okay, now From here you can take the mass inside, it doesn't make a difference, okay, and because it's constant, so it can be inside or outside, and you can take the entire derivative outside this summation, okay. So then you can reduce this form that the change in momentum dpt by dt is the double derivative with respect to time and the summation of all the products of the mass times the position of each of these individual objects, 1 2 3 and so on until the jth object, okay. So here we know that dp by dt is net force, okay, and net force is your basically your m times a, okay. And so here again we can write this as d square by dt square times of m times r, so that is this function right here, okay. So that comes from this relating this equation right here, net force, and that should be equal to this dp by dt value here in 3, okay. So you are just equating 1 with 3, okay, equating 1 with 3, okay. And so that is d square by dt square of the summation of mj rj, okay. That's what we just found out, okay. And so from here you can just ignore that d square by dt square because it is common to the left hand side and the right hand side. And so you're left with an equation that r, the position that we are interested in of this entire motion of this system, right, is equal to 1 over m. So 1 over m can go on the other side and summation of mj rj, okay. And this is your equation to find the position of the center of mass for a system that is composed of many objects, okay. And r is the vector from the origin to the center of mass position right here, okay. So this position is your center of mass, okay. So let's see how this picture actually works out, okay. So it will be more clear to you when we actually use it for an application, okay. So let's take just a situation of two masses. You have mass a and mass b, okay. So now we are asking for these two masses, what is the center of mass for these two masses combined together, okay. They may be attached to each other by some piece of thread or some rod, or they just have some interaction between them that is keeping them together, okay. And so in that situation, where exactly is the center of mass, okay. So again we have to define our x and y coordinate system, so we have to take a frame of reference, okay. And if once we define the frame of reference, this position of the center of mass in the x dimension will be the sum of maxa plus mbxb divided by the total mass, okay. And that is just the same expression here, okay. If r on the x coordinate will be 1 divided by total mass and the summation of the each of the objects. And similarly, if you want to find the y coordinate, then that will be in the y direction of that object plus y direction of the b object divided by the total mass of the system. So let's take an example. You have two masses. This mass has mass m, and let's keep the mass same for our first instance. Both have mass m, okay. So again, the first thing that you have to do is you have to define your frame of reference, okay. So you can just choose your frame of reference by convenience, okay. And I'm going to give you a hint. Let's take this as the y-axis, and let's take this as the x-axis, okay. And let's choose this as the point 0. So now I want to find where is the center of mass for these two objects combined, okay. That means I have localized it on this value on the y-axis. So the y-axis will be 0. So all I have to do is I have to calculate the x of the center of mass, okay. So again, the x of the center of mass will be 1 upon total mass, which will be m plus m, okay. And on the top I have to take the mass times the value in terms of the position of the mass. The first one will be mass, and the position of that object is actually at 0. And for the second object, it is again mass m, and now the position of this object is, let's say this distance is some x, okay. So that will be m times x from this point 0, right. So the distance for the second mass is x, value from this frame of reference. Okay, and for the first mass from this frame of reference, the position is at 0. Okay, so then you will get mx by 2m, and understandably you're getting x by 2, and that is in this I direction of your coordinate system. Okay, that means if you have equal masses, then the center of mass is exactly in the center. Okay, and that's a very simple way of understanding how the system works, right? If you have a ruler, right, and you're trying to balance the ruler with your hand. Okay, so when you keep one finger exactly in the center of the ruler, you will probably be able to balance that ruler in your hand. Okay, but if you move your finger to the left or to the right, then the ruler will just fall, right? So this center of mass position is the position where it feels like all the mass is concentrated to that position. So if you just keep your finger where the center of mass is for a ruler, basically you're putting a counteracting force, and so it is balancing that object. Okay, similarly it goes with a pen. You're trying to balance a pen, so you have to keep your finger. If you want to just use one finger to balance the pen, you have to keep it exactly where the mass is concentrated, and then whatever normal force that you're applying from your finger is balancing your gravitational force from your pen. Let's take the example where now I have increased the mass of this second object to twice the mass of the first object. Okay, so all I have done is I have kept this mass as m, and I have kept this mass as 2m. Okay, so try to solve for this situation. If I have a situation of two masses, one is twice the size of the other, where is the position of the center of mass for these two objects? So first thing we have to do is we have to again choose our axis. Okay, and if we choose our axis, let's choose the axis to be here. Let us choose this point to be 0 of the coordinate system. Let's choose this as positive x, let's choose this as positive y. Okay, and that is again simplicity, right? If you choose something here, right, then you will have a complicated situation, because now you will have some coordinate in y. Okay, let me say if I chose this as my frame of reference, so then again the point which you are saying 2 by 3rd will be here, right? But then you will have some x value 2 by 3, and you will also have some y value. Okay, so a smart decision is made when you're choosing where to keep your 0. Okay, so for convenience we have kept the 0 exactly at one of the objects. Okay, and we could have kept it at this object as well. Okay, so just for convenience I am keeping it here. Okay, and once you solve a lot of problems, it gives you an idea of how to choose your frame of reference point so that the problem gets easier. Okay, so now from this reference point, if I want to calculate the center of mass, the first one has mass m, but the position of that is at 0, so that I'll get 0 value. Okay, and the second mass is at 2m, has a mass of 2m, and the position is, let's say, a distance d, right? And then the total mass is 3m, right? M plus 2m, the total mass is 3m. Okay, that is what capital M is. So I get 2 by 3, right? And m cancel, and then d is the distance. And remember, it is position, you have to define where it is. So it's in the I coordinate. Okay, so 2 by 3 d in I. Okay, because there is no j value. Okay, so remember, this is your unit vector, so you have to define this. Okay, so position has to have this definition where it is pointing. Okay, did anybody notice what we are getting here? The result, this center of mass is lying not in any of these masses, it is lying in between them. Okay, so suppose these masses were interacting at a distance, electric field or force from gravity, right? So it's just holding them in place. So you have found that the center of mass can be outside the particles too. Okay, so that's a very non-intuitive result to figure out. Okay, and we will take an example later on as well. Okay, so let's do a little bit tougher problem. Okay, now we have 3 masses, and I'm going to label this as 3m and 2m and m. Okay, and so now for this configuration of 3 points, let's find where is the center of mass. Okay,
So no information on the distance is given.
they are all equidistant from each other. So let's choose L as the distance. So the total mass is 3 plus 2 plus 1 is going to be 6m, Okay, and now like problems before, since it's a two-dimensional situation, we can decompose in x and y. Okay, so let's say the first equation will be 6m, that is the total mass, and I'm trying to find in the x direction where is the center of mass. Okay, so for the first object which has mass 3m, I can take this as the reference point 0 for convenience. And if I do that, then the position of the first object is just 0. Okay. Now the position of this second mass 2m, okay, if I just draw a straight line here, will be L by 2. So I get L by 2 here. All right. And for the third mass, which has mass m, my position on the x axis is L. Okay, so what I'm getting is I'm getting ml plus ml. Okay, so that I'm just getting 2 ml. Right, so uh, that is what I'm getting. Okay, and if I divide this 2 ml divided by 6m, so m and m will cancel, so I'll get L by 3. Okay, so L by 3 will be somewhere here, I believe. Okay, so that is one position here. I'm just dividing it into three uh, parts, this L. So somewhere along this line, I will see it. Okay, I don't know where on the y-axis. Okay, all right. And in understandably, since most of the mass is concentrated on the left side, my center of mass should shift to the left. So it makes sense so far. All right. Let's do the next equation, which is going to be the y of center of mass. Okay. Remember, I have to use I here. That makes sense. It is on the I axis like this. I have to find the j now. Okay. I should have labeled this as y axis. I should have labeled this as x, positive y. Okay, so let's do again. So on the y-axis, the first mass has 0 coordinate. It is on the point 0. Second one is I don't know where it is because I haven't calculated it. It is this length. Okay, so I will have to use the Pythagoras theorem to find this length, and that will be just your L square will be whatever this distance is on the y. Let me call this d. Okay, so it will be d square plus L square by 2, so L square by 4, okay, L by 2 the whole square, which is this distance. This square plus this square is your hypotenuse square. Okay, so d square should be 3 by 4 L square. Okay, and that gives me the value of d, which will be square root of 3 by 2 L. Okay, so that is my coordinate of this distance on the y-axis for the second mass. So I'm getting 2m square root of 3 by 2 times L. Okay, and then the third mass is again m. So again, the third mass is at 0 in the y-axis, right? It is not on anything there. So again, is 0, and this should be something called j. Okay, so again, this is 0, the second term is 0, 2 and 2 cancel. So I get y center of mass is root 3 by 6, and m will also cancel, and that is L times j. So I'm getting a value of 0.29 Lj. Okay, so if L was 1, okay, so if L is 1, I'm getting 0.29, so I need to know where L is. All right, so let me see, root 3 by 2, root of 3 divided by 2 is 0.86. Okay, so this distance here until this distance value is 0.86. Okay, L, that is just this value of d. Okay, so now I am at 0.29, so 0.86 divided by 0.29, that is just 3 times, so this is 1/3 value here. Okay, so basically 1/3 of this value of d, so right here somewhere along this line. So that point right there, which I have just drawn, right, that point is my value for the center of mass. Okay, so I'm getting x of center of mass is L by 3I. Okay, and y of center of mass is 0.29 lj. Okay, see, the point gets closer to where the heavy masses are, and that makes sense, because the more heavy the mass is on the left side, so the center of mass is concentrated towards the left. But let's stress the point of why we are interested in this center of mass in the first place. Okay, why are we calculating the center of mass? Okay, now it turns out, when an object which has a very complicated shape, okay, and when this complicated shape object is moving, for example a wrench, okay, so if you throw a wrench in air, it is doing a very very complicated motion, right? Because it's rotating, okay, and there might be some vibrations that it is doing. At the same time, it is translating from point A to point B. Okay, so there are multiple types of motion that this object is doing. Okay, so it is very difficult to pinpoint what is happening in this object. All right, but it turns out, in an object like this, there is a point which is this position of the center of mass. Okay, and if you look at how the position of the center of mass, this point is moving in the space, it is doing a very very ordinary and beautiful parabolic motion. Okay, and let me present another example. If you have a diver that is diving, okay, onto a swimming pool, okay, now when the diver is just doing a pure translation, again the center of mass of where the diver is, you see, it is doing a very very predictable motion. Okay, and even if the diver is doing a somersault, this center of mass position, okay, is it's doing a very very ordinary and uh, um, a path that is very parabolic. Okay, so the beauty lies in how this center of mass point is actually moving when the object is moving. Okay, and it should be clear from this example. Okay, so this is an example of the racket that is thrown. Okay, now again this racket is doing such a complicated motion. You see, it's rotating. So if I try to find the motion of this handle, okay, it is very difficult to predict the motion of the handle, because it's basically rotating while it is moving, something like this. You see, just focus on the handle, the edge of the handle. It's doing such a complicated motion. Okay, so that it's moving from left to right, and at the same time it's rotating. Okay, so now to figure out where this handle is going to be is a very very tough job. Okay, to write the mathematical equation. Okay, however, if you look at this point in green, okay, this point in green signifies the point where the center of mass of this racket is located. And if you look at how this center of mass is moving, it is moving in a much more uniform parabolic path. Okay, so it is a very special way that the center of mass is actually moving. So one of the examples of why we are doing this is your center of gravity. Okay, any object. Now, if it is a continuous object, right? Um, if there is gravitational force acting on this object, okay, there is a point in that object that is called the center of gravity. Okay, and what is the special thing about this point? This special thing about this point is that all the mass of this object, you can imagine that it is concentrated at this point. Okay, and when we are trying to decompose forces, and we can just assume that this point where the center of gravity is, it's just a single point, and we can take this complicated shaped oval and forget about the shape and just choose that one point and decompose all the forces that are acting on that point. Okay, so uh, uh, in a human body, the mass of the body is distributed very differently from the top to the bottom. Okay, and the center of mass is actually located on an average. These are average values considering. So it's located 58% above the height from the floor. Okay, so it's not midway, but it is a little bit above that. Okay, and again, the interesting thing you have to realize is how you are looking at the situation, right? If you have a leg, for example, and you have just extended the leg, right, horizontally from the floor, Now the center of mass is somewhere at this point x where we are seeing. Okay, and if I'm keeping the leg on the floor, okay, then my center of mass, it moves. Okay, and now it is below the leg. Okay, I just showed you the example before also. It can be outside the body too. Okay, and actually the high jumpers and pole vaulters, if you ever had the question of why they can jump so high, is because they have developed this technique of jumping, right? And the way they arc their body while they're jumping over this pose is they are trying to reduce their center of mass, and it comes below the pole. Okay, and that's why they do this peculiar kind of motion. Okay, why are they jumping like this? Because it's, again, it has to do with the center of mass and balancing that allows them to jump higher and higher than where they can go. Okay, so again, the technique is developed considering the center of mass. And there are a lot of many examples, other examples in other sports as well, where we we have to balance our center of mass, the center of gravity, so that you can excel at whatever stunt or anything you are doing, right? And there are so many funny videos available as well, where people, they lose their balance because of the center of gravity and they fall. So there are a lot of examples you can go and explore. Okay, so I'm just going to consider an entire solid of some irregular shape. Okay, and again, this object has some I can consider a small mass in this object, some mass I, and then from some frame of reference, this is my frame of reference. Okay, and I can plot out the position of this object. It will be r of I. Okay, and at the same time there will be some center of mass. Let's say the center of mass is located at this position. Okay, and this is your center of mass point. So from the frame of reference, if I am trying to see and locate where my center of mass is, that's where it will be located. So this is my r of center of mass. Okay, so just by the analogy we were doing before, if I want to find the total mass times the position of the center of mass, we had found out that by a relationship, it is just the sum of all the individual masses in the system times the position of the individual masses in the system. Okay, so again, from this situation, what we can say is, if I take r of center of mass, okay, I can write it as m total, and then I can just write it as m of I, r of I. Okay, and from here, what I can do is I can take the derivative. If I take the derivative of this, so take derivative. Okay, so on the left side, I'll get dr by dt. Okay, and that is nothing but the velocity of the center of mass with which the center of mass is moving. Okay, and that will be 1 over m of total. So let's see on the right hand side what you get. So again, you will have individually m of I, and you will have d of ri by dt, right? Or you can write it in simplified form as summation of mi times v of I. Okay, now remember, summation of m of I, v of I is just the total momentum of the system, right? So you are just adding all the momentums. Okay, so we can simplify this and write v of center of mass is 1 over the total mass. Okay, and here you have basically the total momentum of the system, which is thus the summation of all the mass times velocities of each of these individual masses present in the system. Okay, so this is very interesting because now we are getting a relationship of how the uh, the uh, uh, the total momentum of the system behaves in terms of the velocity of the center of mass. Okay, so here we can rewrite this and just say the total momentum, okay, is the total mass times the velocity of the center of mass. Okay, and what are we trying to say? Suppose I do dpt by dt and I'm looking at the change of momentum. Okay, so what will that be? That will be just a of center of mass. because dv of center of mass by dt will be the acceleration of the center of mass. Okay, so now again go back. Remember, we were saying if there is no external force acting on the system and only internal forces are at play, right? And in that case, we know that internally all the momentum will going to get cancelled out. That means your total momentum, this will be zero. Okay, so you will get when no external forces are acting, okay, your dpt by dt will be zero. And what will that mean? That will mean that your acceleration of center of mass will be zero. Okay, and of course, because the total mass cannot be zero. Okay, and what does that mean? That means that the velocity of center of mass is constant. Okay, and this is analogous to your conservation of momentum. Okay, this is the same idea. Okay, so the whole motion of the object is very complicated, but when you look at the motion of this point of center of mass, what we are getting is the velocity is constant, and that is what is happening here. In this complicated motion, the handle is doing a very complicated motion, your racket head is doing very complicated motion, but if you look at this point of center of mass, this point of center of mass, the velocity is constant. Okay, and there is no acceleration that is happening here. Okay, and that is what we have just found out mathematically. Okay, that when no external forces are acting on the system, your uh, acceleration of center of mass will be zero and your velocity of center of mass will be constant.